Question 1. A 2-gram sample of ammonia is mixed with 4 grams of oxygen. Which is the limiting reactant and how much excess reactant is there after the reaction stopped? Okay, so we have two reactants. We have the amounts of both, 2 grams of ammonia and 4 grams of oxygen. So the first thing we're going to do is we are going to convert both to moles. We have 2.0 grams of the NH3, which is ammonia, right here. And the molar mass of ammonia is going to be 14 plus 3, so 14 grams per mole for nitrogen, 3 grams per mole for the hydrogens, and that's going to be 17 grams per mole. So 2 divided by 17 is 0.118 moles of NH3. Now we are going to do the same thing with oxygen. We have 4.0 grams of oxygen, and we're going to divide that by the molar mass of oxygen. But in the equation, we have O2. Whenever we say oxygen in a reaction sense, it's most likely going to be oxygen gas, which is the standard form of oxygen. So we have about 32 grams per mole. And 4 divided by 32 is 0.125 moles of O2. Okay, so now the first thing is complete. We have the moles of how much of each reactant we have. Now, it gives us an unbalanced reaction. The best thing to do is always make sure your reaction is balanced. It's a really good thing to do. So we'll do that now. Nitrogen, there's 1 nitrogen here, 1 nitrogen on the right. So a nitrogen is good for now. 3 hydrogens on the left, 2 on the right. So we can put a 2 right here in front of the NH3 and a 3 in front of the H2O in the product side. What this does is it has 2 times 3, so 6 hydrogens on the left, and 3 times 2 on the right, which is 6 hydrogens. Now we can go back to the nitrogen because we just changed the nitrogen with the coefficient 2. So we have 2 times the N, which is 2 nitrogens. Let's put a 2 over by the NO, by the nitrogen monoxide. So now we put a 2 there. Let's look at oxygen. We have 2 oxygens on the left, and we have 2 oxygens on the right plus an extra 3. That makes 5 oxygens. The way to balance this is when you have an O2, we want to put a fraction of 5 over 2, and then we can multiply the entire reaction by 2 because we can't have fractions in our completed balanced reaction. So our new reaction is going to be 4 NH3 plus 5 O2 yields 4 NO plus 6 H2O. That's our balanced reaction. The next thing we want to do is we want to pick one product, right? We can pick any product we want, and we're going to see, based on the balanced reaction's molar ratio of reactant to product, we're going to test to see which of these reactants create the most amount of product and the least amount of product. Whichever one creates the least amount of product, that's the one that's going to be limiting. Meaning, if it were to react to completion, it would run out first, and there would be some left over of the other reactant that is not limiting. So here's how we're going to do this. Let's test the ammonia first. We're going to take this 0.188 grams, and let's just say we're going to pick the NO, just because we can. We can pick any product, and the same procedure will work. Sometimes in the question, they ask you to calculate the amount of a specific product. If there's a question like that, you definitely should pick that product to test because it'll give you less steps to do in your problem. So now we have 0.188. Let's look at NH3 and compare that to the amount of NOs in the balanced reaction. It is a 4 to 4 ratio, meaning 4 moles of NH3 in the balanced reaction would react to produce 4 moles of NO. So we can use that as a conversion factor. That's a 4 to 4 or a 1 to 1. We can say that 4 NOs per every 4 NH3s. So the NH3s would cancel out, and we're basically multiplying this by 1. So we end up with 0.118 moles of NO produced. Now let's do the same thing for oxygen. The ratio between oxygen and NO is a 5 to 4. So now we need to factor that in. So we're going to have 4 NOs are produced for every 5 O2s. The O2s will cancel, and we will multiply this mole value by 4 over 5, which is 0.1 moles of NO. So they're close, but we can see that the oxygen, if it were to react, would produce the lower number of NO moles. This means that not NO is limiting, O2 is the limiting reactant. So oxygen, we call it our LR, limiting reactant, because it reacts to produce the least amount of the product NO. And another thing we can say is the amount of product created from the limiting reactant is the amount of product made in the reaction. And we also call this our theoretical yield. So we figured out that O2 is the limiting reactant, and we could also figure out how much NO is produced, which is 0.1 moles. We can convert that to grams if the question asks for it, which this one does not, but let's do it anyway. We have the molar mass of NO is 14 plus 16, so about 30 grams per mole, and we end up with about 3.0 grams of NO produced from the reaction. And again, that's based on the limiting reactant. Okay, the next part, which a lot of students find tricky, is how much excess reactant, so not the limiting reactant, the excess reactant, which in this case is the NH3, does remain after the reaction stopped. So we're going to look at our NH3. The easiest way is to use the amount of moles of the limiting reactant, 0.125 moles of limiting reactant of O2, and we're going to use the molar ratio in our balanced reaction to not only go from reactant to product, but we're going to go from reactant to the other reactant. Because what this will do, this will see, fine, if O2 is the amount of reactant that fully reacted, we can find out from using the internal ratio from one reactant to the other how much of the other reactant was needed to make that product. So we're going to see how much of the NH3 was needed in this reaction. And we know from looking at the reactants, it is a 5 oxygen to 4 NH3. So we want to convert this to NH3. We do 4 NH3s, reacts with 5 O2s. O2s cancel out. And we're multiplying this, the number of moles of O2, by 4 over 5, which we ended up doing over here. So we know the number is 0.10. But this 0.10 is not the same as this 0.10 from NO produced. The only reason why we did that is because the molar ratio of oxygen to NO is the same as the molar ratio of oxygen to NH3. If these coefficients were different, the math would be different. So we have our 0.1 moles of not N and O anymore, but NH3 needed. We call this our needed value or our used value. So this is the amount of the excess reactant that was used in the reaction in moles. So all we can do is now take the number of moles that we started out with, which was 0.118, and we can figure out, we can subtract that value. We can have the moles we started out with, 0.118, minus the amount that we used up, would equal the amount left over. So 0.118 minus 0.10 equals 0.018 moles of NH3. And usually for an amount, we're going to multiply this by the molar mass. So times the molar mass of NH3 is 17. So 0.018 times 17 is 0.306 grams. So in this question, to find the excess, to recap, we are going to use our limiting reactant moles. We are going to use the molar ratio to find out how many moles of the other reactant were needed in that reaction. Then we're going to subtract that value, which in this case was the 0.1, from the moles of the other reactant that we started out with. Basically, if you think about it as you have a cup of water, you know how much is in the cup. You know how much you're going to drink, what's left over. We take the total, subtract the amount you drink, whatever's remaining is what's left over. That's exactly what we did here. We took the moles of NH3 that is used in the reaction by using the molar ratio from oxygen to figure it out. And then we subtracted that from the amount that we had originally, amount that was in the question, to get our remaining amount. Let's do another example. So in this case, we have this reaction. Let's balance it first, just because. We have 1 sodium, 1 chlorine, 2 chlorine, so we can put a 2 in front of here. And that makes us put a 2 in front of the sodium. we have one lead, and one lead, and we have 2 nitrates on the left and 2 nitrates on the right. It's very important to keep these polyatomic ions the same and balance them as complete groups rather than the nitrogen and oxygen individually. That makes your life a lot easier. So the question, how many grams of lead-2 chloride are produced from the reaction of 15.3 grams of NaCl and 60.8 grams of lead-2 nitrate? What is the limiting reactant and how much excess is left over? So the same type of question. Now let's do the same exact process. First, convert it to moles. So we're going to take our first reactant, which is the NaCl. We have 15.3 grams of it, dividing by the molar mass of NaCl, which is 58.44 grams per mole, which equals 0.262 moles of NaCl. We will do the same thing with the lead-2 nitrate. We have 60.8 grams. We're going to divide that by the molar mass of lead-2 nitrate, which is 331.2. 60 divided by 331.2, we get 0.183 moles of PbNO3, 2. So now we're going to do the same exact thing. We're going to pick a product, any product. Well, we're going to pick a product, but this time we are being asked explicitly how many grams of lead-2 chloride are being produced. So to make our lives easier, we're going to pick lead-2 chloride, which is this product over here. We'll call it product 2. So we're going to use the molar ratio in the balanced reaction to figure out how many moles of this lead-2 chloride would be produced if each of the reactants reacted completely. Whichever one produces the least amount is the limiting reactant. For NaCl, the molar ratio between NaCl and the lead-2 chloride is a 2-to-1. So 1 PbCl2 is made from 2 NaCls. The NaCls will cancel out. So we're dividing this by 2, 0.131 moles of PbCl2. We're going to do the same thing for our lead-2 nitrate. Our molar ratio from lead-2 nitrate to lead-2 chloride is a 1-to-1. So we have 1 PbCl2 for every 1 PbNO3, 2. That cancels out, and we end up with the same number, 0.183 moles of PbCl2. Okay, which one produces the least amount? 0.131 is the least amount, and that's produced from sodium chloride. So sodium chloride is the limiting reactant, NaCl. I'll put Lr right there. How much excess is left over? Same thing as before. We're going to use the limiting reactant, 0.262 moles of NaCl, times the ratio of that reactant, NaCl, to the other reactant, the lead-2 nitrate. It is a 2-to-1. So 1 mole of PbNO3 is reacting with 2 moles of NaCl. This means that how many moles, we're basically figuring out how many moles of the PbNO3 had to react with the limiting reactant in order to produce this product. So we will divide this by 2, and we end up with 0.131 PbCl2. 0.131 PbNO3. Now again, it is just a coincidence how the number of product produced here is the same, or it is just a coincidence how the number of moles of the excess reactant used in the reaction is the same number of moles of the product produced. The only reason that is because our PbCl2 has the same coefficient as the PbNO3. So this is the amount used. So this number, this point, in this case, the 0.131 moles of lead-2 nitrate is used in the reaction. Now, the question is, how much did we start out with? We start out with 0.183. So 0.183 minus 0.131 equals 0.052 moles of that reactant, PbNO3 2, and that number in grams would be 0.052 times the molar mass of PbNO3 2, which is 331.2, and that would be 17.22 grams. So that's how much the excess is. Okay, let's do another one. We're going to do two more. How many grams of magnesium nitride product can be made from the reaction of 35 grams of magnesium and 15 grams of nitrogen? How many grams of excess reactant remain? Okay, same type of question. Let's balance it first. 1 magnesium on the left, 3 on the right. We'll put a 3 there. Nitrogen, we have 2 of them on the left, 2 of them on the right. We're good. So we're done. So let's figure out what is made. We have 35 grams of Mg. We're going to divide that by 24.3 grams per mole because that's the molar mass of magnesium. This is going to be 1.44 moles of Mg. Next, nitrogen. We have 15 grams of nitrogen, N2. We're going to divide this by the molar mass of nitrogen 2, N2, which is not going to be 14, but 14 times 2, which is 28 grams per mole. This is going to be 0.536 moles of N2. So now we're going to use the molar ratio again to figure out the product. So the molar ratio of the product to magnesium is a 1 to 3. So to make product, we will divide this by 3. So 1 Mg3N2 divided by 3 Mgs. Mgs cancel out. We end up with dividing this by 3, which is 0.48 moles of Mg3N2. Same thing for nitrogen, but in nitrogen's case, it is a 1-to-1 with the product. So 1 mole of Mg3N2 per every 1 mole of N2 gives us the same number, 0.536 moles of MgN2. Okay, so in this one, the limiting reactant is the magnesium. So magnesium, limiting reactant. It produces less of the product. How much is that product? We can multiply it by the molar mass of Mg3N2, which is 100.94 grams per mole. 0.48 times 100.94 is 48.45. 48.45 grams. Okay, that's the amount produced. Next part of the question, how many grams of the excess? So what we're going to do is find the amount of nitrogen that was used in this reaction. So we'll start with the amount of magnesium. We're going to multiply it by the ratio, which is a 1 to 3. 1 to 3. 1 mole of N2 for every 3 moles of Mg. Moles of Mg will cancel, and we will get 0.48 moles of N2 used. Okay, that's the amount used. We're going to take the amount used and subtract it from the amount that we started out with, which was 0.536 minus 0.48, which equals 0.056 moles of N2. We're going to multiply that by the molar mass of N2, which is 28, and we get 1.568 grams left over. Okay, we should be getting pretty good at this by now. Let's do one more, and this one's a little bit more complicated. It's not repetitive. Well, same process, but we have 2 reactions now. So let's read this carefully. A reaction container holds 5.77 grams of P4 and 5.77 grams of O2. The following reaction occurs. So we have this reaction. If enough oxygen is available, then P4O6 reacts further in this reaction. Okay, so keep in mind, we have 2 reactions now, and they're both different. We're going to figure out what's the limiting reactant for the first one. We're going to figure out how much product is produced, and that will lead us to our second reaction, because the product from our first, P4O6, is the reactant in our second. So we have to find out the amount of P4O6 to see if the second reaction occurs. And because it's in the question, we can assume that it's probably going to occur. So let's do the same thing we did for the first reaction. We'll break it up into one thing at a time. So what is the limiting reagent for the formation of P4O10? So it's asking at the end, Don't get confused because P4O10 is the product of the second reaction. This means that we can kind of assume the first reaction goes through and there's enough oxygen to go through the second reaction. But let's find the limiting reactant for the first reaction and then find the amount produced from the first reaction so that we can find everything we need to know. So first, let's convert to moles. Well, let's balance. First, let's balance. So we have, I'll write both equations here. P4 plus O2 yields P4O6. Second reaction, P4O6 plus O2 yields P4O10. Let's change the color. So let's balance the first one. We have 4 phosphorus, 4 phosphorus. We have O2 and O6. Let's put a 3 right there. Second one, we have 4 phosphorus, 4 phosphorus. We have 8 oxygens here, 10 of them on the right. Let's put a 2 right here. If we do that, we'll have 4 plus 6 is 10. Okay, let's work it out. So what's the limiting reactant for the formation of let's find the moles first. 5.77 grams of P4. The molar mass of P4 is 123.89 grams, which is 0.0465 moles of P4. The same thing for the other reactant. 5.77 grams of O2 is going to be divided by 32 grams per mole. 5.77 divided by 32, 0.180 moles of O2. So let's figure out how much of the product is produced by first finding the limiting reactant, whichever one produces the least amount. So the ratio of P4 to the product is a 1:1. So we can just do 1:1. And I'm going to speed it up a little bit. We'll go 0.0465 moles of P4O6. We will do the same thing for the oxygen. We know for oxygen it is a 3:1. So 1 mole of P4O6 for every 3 moles of O2. So we're going to take 0.18 divided by 3, which is 0.06 moles of P4O6. All right, in this case, the P4 is the limiting reactant. It completely runs out and it produces this much of P4O6. We're going to use that in the next reaction. Now what we have to find is in the next reaction, so we're good with the P4O6, we don't know how much oxygen is left over. And it says if enough oxygen is available, then the P4O6 will go through a further reaction. We have to find out the excess after some of this O2 was used up, how much is actually left over. So we're going to use the amount of P4, the limiting reactant moles, just like we've been doing. 0.0465 of P4, and we're going to find out how much oxygen was needed to make it, or was needed to react with it. We know it is a 1:3. So again, we're going to take this and we're going to multiply by 3, because we're converting this to the amount of O2. So 3 O2 divided by 1 P4, because it's the reaction ratio is 3 O2s for every 1 P4, and we get 0.1395 moles of O2. So this 0.01395, that many moles of O2 was needed to produce the 0.0465 moles of P4O6. So it's based on the limiting reactant, right? So now the excess reactant is going to be subtracting that amount of O2 that was used to create the product from the amount of O2 that we started out with, which was 0.18 moles, minus 0.1395 gives us 0.0405 moles of O2 left. Okay, so now we have everything we need. I boxed everything we need. We have the amount of O2 that is left over from the first reaction in moles. We have the amount of P4O6 that is produced from the first reaction in moles. So now we're going to use the molar ratios and figure out the limiting reactant again and figure out how much is produced again for the second reaction. So let's do that. Let's start with the P4O6 first. We have 0.0465 moles of P4O6. That reacts in a 1-to-1 ratio. So every 1 PO4 creates P4O10. So it's a 1-to-1. And that's going to equal 0.0465 of P4O10. We'll do the same thing for oxygen. 0.0405 of O2 times the molar ratio is a 2-to-1. 2 oxygens make 1 of the product. So it's going to be 1 P4O10 divided by 2 oxygens. Oxygens will cancel. We're dividing this by 2, 0.02025 amount of P4O10. All right, so in this case, which one produces the least amount? This is the least amount, the bottom one. So this means that oxygen is the limiting reactant. So the limiting reactant for the production of not the first reaction, but for the second reaction, which is the formation of P4O10, is O2. That's the limiting reactant. So now, what is the mass of P4O10 produced? It is this many moles, the amount of moles produced by the limiting reactant. And we're going to multiply that by the molar mass of P4O10, which is 293.89, which is 5.95 grams of P4O10. So that's how much is produced. All right, so that's it. For in a nutshell, limiting reactant, it's not too bad. You first need to test each of the reactants to find out, using the molar ratios, which one produces the least amount of product in moles. After you're done with that, you want to go back and you want to see how much of the excess is remaining. All you do is use the ratio of the amount of moles of the limiting reactant to the other reactant, which is not limiting, finding out how much of that other reactant is used to react with the limiting reactant. Once you have the amount reacted of that non-limiting reactant, you subtract that amount from the total starting material of the non-limiting reactant, just like we did in these 4 examples.